All right, so I'm going to go ahead and get started a little bit. I'll tell you what to write, all right, what to jot down, but some basics about the fundamentals of electricity we got to get down. We're going to go all the way back to talking about an atom. You don't need to write this down. I think you know this from your other science classes. So the center is called the nucleus. What's in the nucleus? Can you tell me? Karen, you're pretty good with this. Protons and neutrons. Very good. Okay, so you got the center, which has got the neutrons and the protons. All right, and then you got to picture something inside. So you got a ball, and then you think about the two things inside there like it, and there's probably usually going to be an even number of protons versus neutrons, usually, okay? So they're not positive or they're negative. The neutral ones are nothing. They are absolutely no charge whatsoever. And then the protons are the positively charged atom, particles of the atom, okay? And then around that, this is the money right here. This is what's doing all the orbiting and the circling and everything around it. And those are negatively charged electrons. And there's a certain law, I'm not going to go over all the laws, but the number of electrons that fit into one of these outer rings, right? And then they fill up, and then they got to make another outer ring, all right? So they keep going on and on and on like that. So those are going to orbit around, and they say orbit, but they don't really. Some of them come real close to the center, and then they come real far away, and they're moving all around, you know, not really like that from what I've seen on the NASA channel. They showed a little thing where it looks really random and kind of crazy. It almost looks like a I don't know, it's pretty wild when you see it, their interpretation of it. All right, so going down now, so you got the atoms and then we got molecules. And now they're going to arrange these atoms into any form to form something. It could be a compound. What's the most common compound that they're always talking about you forming? You know, you take oxygen, hydrogen, what do you make? Water, H2O, yep. So you got the atoms that form. All right, so we're going to take these, and then you got your oxygen atom, and then we only got one. All right, one proton, neutron, and electron. So that's the hydrogen, the most basic. All right, and then they go up to this one with the oxygen. You combine them two together, and that's the one that they talk about. Right. So there's something happening there where it's combining both the molecules together to form a compound, which is in this case going to be H2O, water. All right. Now let's talk about the positive. If we have an equal amount of protons versus the electrons spinning, if it's 8 and 8, like what you just saw with the oxygen atom, then that's going to be a balanced, all right? That's going to be uncharged. It's not going to have any charge whatsoever. But if it has one more than the other, like if there was one more negative electron on that outer ring, right? And then compared to the nucleus in the center, like there was 7 proton neutrons and 8, we got an unbalanced charge of more negative than positive, so that's going to be a negatively charged particle. And then it can go the other way. Let's say you didn't have as many on the outer rings as you did in the center of the nucleus. That would be the other way. The charge is now positive. Okay, so you can have a positive and negatively charged atom on that. And that's where we get this, right here we got the balanced charge because everything's even. If you added up all the electrons, now that we've combined the two atoms of hydrogen and oxygen together, you see that you got 10. And that's a neutral charge. So that's why when you touch water, it doesn't shock you. You don't get shocked. There's no difference between the polarity, difference between the charges. So, but if you take one of these away, now you have less negative electrons than you do in the center of the positive charged particles, and now that's a positively charged atom. And then going the other way. All right. So this is where we have conductors. Conductors have those extra electrons on the outer ring, and they're able to transfer that energy really easy. All right? Copper atoms have this thing called a valance electron. It's a free electron. So they're going to be, see this extra one right here? What is that going to be then? If it's got one more here than in here, what's it going to be? Negatively charged, okay? But let's see if it's got 29 on the outside and 29 on the inside. So they got them all in there. You got 29 electrons on the outside. So this thing's going to orbit around. They call this one a valance electron. All right? Do me a favor, real quick, just draw this, all right? And just draw a center nucleus. You don't have to put all the dots, but put the rings, and then kind of put that there's one outer ring that has this extra negatively charged, and label it a valance electron real quick. All right? That's kind of important that you need to know that, because this is what we're doing with the electricity. We're moving this one. Whether it's direct current, it's going one way, or alternating current where it goes back and forth. Okay, so we got that valance. That's an extra negative electron that's orbiting around the outside. So that's what it looks like there. And then when I take other copper atoms, like you got your copper wire, and all these atoms are lined up in a row, should show them here in a second. All right. So they're going to show you now where it shows with the electrons moving from conductor to conductor. So we can do that a bunch of different ways. We can force the atom to move with friction. That's like the balloon. You take the balloon, you rub it up against the head, you're creating a little bit of static electricity. We could do it with chemical batteries, all right? And that's when you take them apart. You see all the alkali coming out all over your hands because the battery died and it kind of got a little corroded on the end, all right? So the chemical reaction kind of almost caused it to come out of the battery there when they die. And then the one that we use primarily for most of our power is going to be magnetic, all right? So we do that with a generator, and that's called induction. So we can induce power into a wire. So there's going to be a couple more ways. I think on your other test they showed you where they can crush crystals. You take quartz. That's how they're powering up the batteries. You know, they're using that with time. They crush the quartz, and that'll create a little bit of power. And then we can also do it with flame. So if I had two different metals, sort of like with the limit switch I showed you last week, if I heat it up with two different metals, that creates a small amount of millivolts, a little tiny amount of electricity on it. So here we go. We got our 3 copper atoms. All right, they're orbiting around. And what was this one out here called? The valance. So we're going to charge one. So one's going to jump. So boom, I knocked one out. Well, now this outer ring's missing that electron that just got pushed down the line. So what's going to happen here? It's going to be a chain reaction. You're going to get this one to hop over to the other one, and this one's going to hop over to the other one. So now we've got current flow because we were able to, and then something from back here is going to keep going. You see how that works? That is just like, let's say that this is a battery, and what you just saw here was this. So like if I turn this upside down, you're going to see those electrons moving from one side to the other. But what's eventually with a battery going to happen? It's going to die. It's going to lose all the electrons, all the charge is eventually going to wind down, and you're not going to be able to run anything anymore when you don't have that movement of electrons. It's not powering up anything. All right. So then what do you got to do? You got to change the battery, or in this case, I'll just turn it over, and now I've got the electrons moving again. So that's just like this, but you can't see it. It's such on a small scale. You would need something like a meter to read, one, if you had the potential voltage, the thing that knocked out that original electron, all right? And two, depending on how fast these electrons are bumping from one atom to another, it's going to create a magnetic field, which you can only see with a meter like this, right? It's called an amp meter, and amps is what they use for current. Amps and current kind of go hand in hand. So any questions about the atoms? You see, this is what's happening on a very small molecular scale that you can't see, but that's how we do it. And then the way that would be direct current because it's going from negative to positive, right, all the way over to do the work somewhere. And then eventually, if this thing back here stops running out of power, then you're not going to get anything anymore. It's not going to do anything more. The current will stop flowing, and whatever it is that you got powered up will die. Now, alternating current is a little different. Alternating current, that's when Tesla came up with his generator that figured out, hey, you don't need to move all these from one end to the other. You can just move them about 5 spaces to the right, and then move them 5 spaces to the back, and that'll create that current as well. And you can move those atoms. So that's like this one here. So direct current means it's going to run out. But alternating current is like where they take a generator on an end, and that generator causes all those valence electrons to push one way for about a second, and then the other way another second. And actually it happens about 60 times a second, where these atoms will go, these electrons in the atom will go from one to the other. So that's pretty much what they're doing with these electrons on alternating current. They're not going in one way. They're going one way, and then they're going back. And they do that about 60 times a second. You know what they call that when it happens 60 times in a second? Linus? You don't know? No? No? It's called hertz. 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 You ever heard of hertz? Like when you're buying a TV? What kind of TV do you want? Hertz? HD, yeah, but okay, so I got a 720, and then I got a 1080, and then they also came originally with like these 60 hertz TVs, and then they were 120 hertz TVs, and then they were 240 hertz TVs. What's the difference? Hey, if it's 1080p, what's the difference between a 1080p 60 hertz and a 1080p 240 hertz? Anybody got the difference in those TVs? You ever seen the difference? No, not necessarily. Well, okay, yeah, kind of sort of like lag. All right. If you had a TV screen that was blinking 60 frames a second, 60 times a second, all right, how would that picture look compared to something that's blinking 240 times a second? Clearer. Yeah, really clear. Yes. That's the difference in the hertz. See, your eyes, this light, everything's strobing really fast right now. But it's so fast, our eyes can't see it. The same thing happens with that's what they call the hertz. When this thing flows from one side to the other, back and forth, that's like 1 hertz. And that happens 60 times a second. And on those high definition TVs, it's a smoother picture because it's faster than the 60 hertz that's going to be a little bit more choppy that you couldn't really see with your eye, but you can kind of make it out sometimes, especially when it jams up. Watch the clock because we got the assembly at, we got to leave here at 40 after. All right, so copper is a good conductor because of this valence electron. Aluminum's also good. What else do you think would be really good? Huh? Ohms? Ohms is something different. But what other metal? Ohms I don't think is a metal. Gold. Gold's the best. Yep, gold's actually one of the better conductors because it's got really good conductivity to where it can flow that electricity. So they came out with this thing called Ohm's law. You're going to see about it. Right, this is like the BTU where it takes 1 BTU, 1 pound of water, it'll raise it 1 degree Fahrenheit. This is 1 volt will push 1 amp through 1 ohm of resistance. So you got to get familiar with these words. Volts is going to be my potential. Amps is going to be that flow, that current, how fast it's flowing on that electron. And ohms, well, that's like opposition. So as it's trying to move through the wire from electron to electron, it's got something to work against, right? It's got some resistance. So that resistance we can measure, and we measure resistance in ohms. And then they got a little wheel that goes with it. Other words that they'll use with volt, electromotive force. This was Volta. Volta came up with this, all right, and this deals specifically with the movement of those electrons. But another way of writing it is the EMF, electromotive force, equals intensity, which is that current flow, times the resistance. So we can figure out some stuff with these movement of electrons by doing some math. And another way of putting it is E equals I times R. And then I can write it several different ways. You don't have to write the X, the times. You can just write E equals IR. Because that's what it's going to multiply to. You're going to need to know that the V is really going to be an E in our pie chart. Volts and I'll think of energy. Volts is energy, electromotive force, same thing. And then I is going to be our amperage, the intensity of the flow in the wire. And then resistance is going to be ohms, but we don't really put a big O. They kind of use this Greek symbol for omega, ohms, but in the pie chart it will be R. So you'll see E, I, and R, and this is what they mean. And then they're going to show you one other way here. Let me see if we can move it down. Volts, amps, resistance. Everybody good? No? I'm going to give you 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We'll come back to it. All right? Just want to move ahead a little bit. So here's the way it works out on the equation. You can write it E equals I times R. So you're going to be given usually 2 of these numbers, and then you're going to have to figure out the third. Usually we use it to figure out our current. So solving for I, I'm going to actually show this with you. You don't have to write all this down. We're actually going to do this. So if I had one or the other, I could switch and flip-flop them around. So here they've taken it where E equals I times R. Well, they divided it now from E divided by R. They just move it around a little bit. this is kind of the most confusing way to learn Ohm's law. All right, so they show you all the different ways, usually in the book. The better way is to use a chart, and I'm going to have you draw it out. All right, wait, we got a little math. We're not going to do the math yet. I'm going to show you the chart first. We're going to skip ahead, skip ahead, skip ahead. Don't look at that math. Don't look at that math. Don't worry about it. It really should be ahead of this slide. Ah, they don't have it. There it is. All right, draw this disc out. So you got a circle, cut it in half, put the E on top, the I down here, and the R over on the right. Anybody ever seen this before?
No. Yeah. Besides when you're picking who wants the most of the pizza.
That's funny. Funny man's got jokes. Yeah. So E, Eric would probably get most of the pizza. Now Ingrid ain't getting nothing, and there's Rob right there, boy. All right, so no. So E is electromotive force, I is the intensity, and R is the resistance in ohms. Now look, I showed you the word writing of all the way they could do the math. This is why I want to show you the pi, because if you needed to find I, you just cover it up with your hand, and that's going to be E divided by R. All right, so you don't need to memorize all the different combinations if you can just do the pi, right? Because they're all right here for you. And then if you wanted to find the electromotive force, the volts, then you would need to find I times R. And then if you didn't know the resistance value of something, you would cover that up here, and what would that be?
E divided by I.
Yeah, so that's easier to understand this way than all that slides I just jumped up ahead of you. So we'll put that one ahead for the next class so that I don't have to skip through about 10 slides. And now we could go back, and I bet I could give you some values like 120 volts, right? Let's just do one real quick. Let's say that you had, and I'll do it on the smart board here. Let's say that you had 120 volts, and it was pulling it was pushing that voltage through a resistance value of 10 ohms. What would the amperage be if I clipped it around the wire?
12.
Yeah, so 120 divided by 10, I would expect if I hooked up the amp probe to find 12 amps of current running through that wire. Right? So that's the way they do that math. And then they can manipulate the combinations a couple other different ways. We'll pick this back up when we come back on to Thursday. So for now, we got to get ready to go to the assembly. You can leave all your stuff here.